Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today we're doing something I'm calling quick maths. Quick calculations for humans and for computers, that's the intro. Welcome to the stream, nice to have you with us. I'm going to give it a minute for people to join the stream before I start doing stuff, and that gives me time to do some shout outs and chat to people like Erin, who's here in chat. Hi Erin. It's just me on the stream today, but I have a researcher, which is a new thing. Somebody else has done the research for me, so that the preparation is not all on me this time, which is pretty exciting. I saw a few people were waiting for this to go live, so I figured maybe people don't have so many mocks anymore. Have mocks finished? Are you done? I don't want to say that too soon, I guess. Hi to Jay, hi to Herb, hi to Oscar as well. Yeah, I don't want to say that too early with mocks finishing, in case somebody is watching this in between mocks, and oh gosh, terrible, isn't it? Somebody's done a really hard A-level paper. Oh, I'm sorry, you found it hard. Even my Cambridge friend. We've all got that one Cambridge friend, right? If you don't, hi, I can be your Cambridge friend. Right. Hi Josh, and hi Miles. Hi everyone. Right, good. I've got some adverts on the screen. One of them you've seen before. It's for the Matt live stream with me. It's one of the things that's got a lot of my time in over the year. Matt Livestream is a series of 2-hour live streams on this channel, starting quite soon. Hi to Mike, hi to Natty. Matt Livestream is going to be coming soon. You've already heard about that. I've also got an ad for a summer school. It's at Cambridge. It's Cambridge. I know this is an Oxford live stream, but hey, I saw an interesting looking summer school at Cambridge. If you're a female UK Year 12 student, then hey, maybe try and find this on the internet and find out about it. It's a summer school for you. I know that's not everyone. There's some like Venn diagrams there from last week, right? But that's why I've stacked it with Matt Livestream, which is for absolutely everybody. Hi, Echo. Right. Okay. Never really know how this is going until it's going, and it's currently going. Let's find out how your day was. How was your day, chat? You having a good day? There's somebody in there who just, as soon as the poll launches, hits the 5-star button in, I swear, under a second. Whoever you are, you're clicking that very, very quickly. Well done. So this is a fun game I play at the start of each one. Try and get a bar chart, because, hooray, bar charts, to work out how people's days are going. I'm always looking out for people who vote for the lower options, because we've all been there, right? We've all had terrible days. Maybe doing some maths is the right thing to do. Today the bar chart is coming out in a sort of linear sequence, like this, maybe arithmetic sequence. Look, it goes. That's a very nice staircase picture there. Is that spot on? Whoa, clip it. That might be spot on. Multiples of 7. Two questions behind the poll in chat that you can't see on the screen right now. Is Matt Livestream going to be fun? I'm going to try and make it fun. We're doing a mix of problems. There's a bit of A-level revision in there, which will probably go off on tangents and revise A-level through the lens of looking at other stuff as well. And then when we're looking at past papers, we might talk about the sort of maths that's going on inside those questions as well. So it's not going to be fully like a classroom going through past paper questions. Did you get this right or wrong? Tick and cross. It's not going to be fully A-level revision like a cramming for a school exam, but we're going to try and do a bit of both, and slightly more focused on getting through some named topics rather than this, which is a little bit different. Miles has claimed being the first person in. It's not a race, I suppose, but Miles is. It's not a race, but Miles is winning. That's a Kaiser Chiefs lyric. Anyway, somebody's asked if step questions live. They've asked a step questions live feature. Final rating there, almost 4 stars, which is pretty good. If you're having a 4-star day, great. Their question is, does step questions live feature? I think they mean, is there like a live step show? And I'm not really aware of one. There's step resources that you can join in with. So if you're looking for some sort of step live stream, then there might be other things as well. Will the Matt live streams include Matt past papers? Yes. And they will be spoilers beforehand. It'll be really clear which questions we're doing. So, spoiler alert, this year, following some feedback from current students, we're looking at more past paper questions. I used to pick and choose which past paper questions we were doing, and then we would do a couple of complete papers at the end. This year we're stepping it up to look at more of the past paper questions. The Mat livestream's been running for a few years now, and it's something like 40% of first year students say that they took part in it, and their feedback from people now at Oxford is that they were doing more past paper questions. So we're going to put more of those into the Mat livestream so that they're there. That's the plan. There's a very rough timetable. If you look at the Mat livestream page, it's kind of under construction. There's a very rough timetable of how we're laying out the schedule for that. And to answer Mark's question again, it's going to hopefully be a little bit more fun. How do we feel about, so Edward's here. Hi Edward. No need to apologise, we've just been doing a poll and talking about event things on screen here. How do we also feel about Olympiads in other subjects? Can you make it relevant? Can you explain how it was a good experience for you and how it's helping you for university? So there are loads of these other physics Olympiads. Informatics is a thing. I've heard of the chemistry one as well. Gosh, I can't remember if I did any of these. I think I might have done the physics one once. I can't remember. It rings a bell. So the story is always, if it's relevant and if you explain how it's giving you experiences that will help you be a better student on course, then feel free to tell us about it in the personal statement. Timings for Mat questions, we'll get there when we get there. My general advice is that short questions about 6 minutes, long questions about 22.5 minutes, but that's slightly based on surveys of first years. That's the sort of advice that I'm going to try and pepper all the way through the Mat live stream about how long people are spending on questions. We got data because we got people who did this pink and purple Mat live stream thing. I shouldn't say it like that because they did it when it had a different colour scheme. Anyway, never mind. They did this pink and purple Mat live stream and now they're here, and I've been listening to them about how I should change it. It's more episodes this year as well. Good, right, this is an extended plug for a live stream that's coming up in the future, which is a bit weird because we're currently in a live stream situation, so you might think, I could just get on with doing a live stream rather than talking about a different live stream. Oh no, when are the maths department open days? They were a couple of weeks ago, I'm really sorry. So we run these things in April. We're running more though at the end of June. In fact, the whole university is running these open days on 28th of June, 29th of June. If you're watching this in 2023, at time of recording, that's about a month from now. 28th of June and 29th of June. And that's not just the maths department, every Oxford department and college is doing something for that. No booking needed for the maths department things for that day. It's first come, first served. First people to, I guess, anyone welcome. It feels dangerous saying this to the whole internet, right? But hey, party at our place. That is very dangerous. I should not even joke, right? I don't know what. So is this, people are asking about that the one particular A-level paper which I haven't seen and I haven't done, so I can't really help you with that. You said it's harder than Mat, which, oh gosh, 9709/12 of June 2023. Wait, that's the future. That's the future. Are you from the future? Tell us more. And somebody wants to know which colleges I would recommend or recommend against. I think all of the colleges are great because they get you access to the same maths course at Oxford. Right, a little bit of admission stuff. Is anybody else doing further maths A-level next week? How about you think about that? Are you doing further maths A-level next week? Gosh, maybe some year 13s in chat? Have we got any year 13s in chat? I sort of wonder if people hang around for year 13 or whether, once you got a university offer, I get live streams. Okay, here's something to try while you're thinking about that. While I try and work out what 9709/12 June 2023 means. Here's a thing to try. I'll read it out. It says, choose a positive whole number x. I'd like you to work out x plus 5 over x, all divided by 2, and then call that x, replacing your previous x. Repeat those steps. So keep working out x plus 5 over x, all divided by 2. I'd like you to let me know what happens. What can you see? What can you notice? And what do you wonder? Can you explain what's going on? I've set up at the bottom here, if you've got a calculator with an answer button, like that, then you can do this on a calculator, and it's quite satisfying to do it on a calculator because you can type in this kind of calculation using the answer key that makes it a lot faster, which is like mashing. Oh, June is the exam season. That's right. Okay, it's not a reference to the exam being in June. Right. Okay. I now know which paper you're talking about. If you can't come as an open day as an international student, you could email the department. Some departments might be able to sort something out. Hey, someone in chat says they're going to, well, they've got offers from loads of things. Oxford CS and University of California, San Diego. Wow, wow, wow. Cool. Further maths next week. We've got encouragement from chat about further maths. We've got a number in chat which I think is about this. That's a repost. Oh, it's which one do I suggest you go to? Up to you. I mean, hang on, no, one of them is Oxford. I'm at Oxford. I have this kind of bias, right? That you've got an Oxford offer, chat, this person's got an Oxford offer, do you think they should accept their Oxford offer? Should we turn this into fraction of x squared plus 5 over 2x? Oh, you could do. Could do, maybe it's less dividing and multiplying, who knows? So people maybe with the help of calculators or something have got a number in chat, and excitingly, I didn't tell you where to start. You might have chosen different positive numbers x, but so far the numbers that people have put in chat are pretty similar to each other, right? There's a prediction of what that number is there as well. So I guess the question of the exercise really is, what's going on? Why have you all got the same number as each other? I was going to ask, what is that number? Somebody in chat's already guessed or told us, I suppose, that it's square root of 5. We use our rational function knowledge, or even our rational knowledge of functions. There's a slightly different number here, which I'm going to post as well. And a question, how do I not fail step, brackets 1, 1? So is that a 1, 1 offer for step? Step's got a really good support program. It's a bit like the Mac livestream, but it's for step. So if you see this, if you look out for, well, the website's really easy to say, it's maths.org/step. That's got some really good resources for building up to past step questions. Well, let's try past step questions. Step is, in some sense, predictable in that the format is very stable and there's lots of past paper questions. In some sense, unpredictable because the questions are always new. It tests a huge range of mathematics. You might like to look at this list. This is not really a step advice live stream. This is more of a, what's this kind of live stream? Yeah. I'm just showing you this advert for where I'm about to do three months of admissions, and here's a maths question, but from an exam. But I've got 2 or 3 weeks left of, this is kind of weird. What's going on here? At least let me enjoy the 2 or 3 weeks of what's all this. Is there a link between the previous fraction and the next denominator? Thank you, Johnny. This is the first person in chat to mention fractions. If you started with a whole number, you will see fractions. Is that obvious? I'm not sure that's obvious. Okay, if you start with a fraction, you will see fractions. And Johnny's got an idea about the fractions. If you've been putting this in a calculator, well, my calculator gives up on the fractions quite fast. So I'm not going to be able to check Johnny's hypothesis with my calculator. What's the relationship of those fractions? I do want to investigate that as well, so that's good. Root 5 kind of makes sense. Root 5 gives back root 5. Okay, if the number you thought of was the square root of 5, then interesting. Then this x here would be square root of 5, and so would that. This is the average of those two things. So the average of two things would be square root of 5. Oh, there's almost put iteration in here. If you like sequences and series, then you might like to write this as x subscript n plus 1. Yeah, I guess I could have written it out like a sequence, right? X n plus 1. If you like recursion, you might like to write it like this. X naught is anything you like. It's greater than 0. And then do something like that. Yeah, good. Alternative notation, very nice. We've got an x squared and a 5 in there. Oh, if you start with a negative number, what happens? It's a good question. So exploring outside the box there. Starting with negative goes to negative square root of 5. Something about x squared is 5, and depending on x naught, depending on your first thing, maybe you hit positive root 5 or negative root 5. I guess I'm interested in what's happening along the way, which is why I made such a big deal of Johnny's comment about the fractions that you get out, because it sounds a bit like Johnny's looking at the sequence along the way. It sounds like everybody's getting to the same answer at the end, up to a plus or minus sign at the front, which I've got further questions about, but the journey along the way is interesting. So Miles has stuck this into Desmos and found the turning points. I'm fine, yeah, okay. If you've done the bit of A-level maths or equivalent where you start learning to differentiate things, you can maybe find that it's got turning points where 1 minus 5 over x squared is 0, which is a plus or minus the square root of 5. Cool. Which is maybe relevant. It's hard to say, I think. If you solve that, okay. That sounds nice. So Erb's attempt here is to describe this behaviour that other people have seen, that if you're at square root of 5, you get back to square root of 5. You get stuck in a loop with square root of 5s. Erb's attempting to explain that by sort of like looking for this number. Look for x with x plus 5 over x over 2 is equal to x, and that's some sort of like quadratic equation which you can go and solve. You get x's. Something like that. Why does it need to be positive? Yeah, so there's something going on with positive and negatives, right? There's two solutions to this quadratic. Which one you see as a result of pressing equals on your calculator a lot or doing this calculation quite a lot. It needs to depend a little bit. But luckily I told you to start with a positive number, and that seems to be good enough. Okay, what else can we see? If I choose I as my starting number, we have this sort of running joke in chat that we love higher dimensions and we love complex numbers. If you put I, makes the sequence divergent. Gosh, what have you done? What have you done? I plus 5 over I, and then you've tried to, I guess you've had to simplify that to make it minus 4i, or something like that. Yeah, I is a complex number. Divided by 2 is minus 2i, so yeah, it seems pretty bad. Seems pretty bad. Yeah. If you've already seen Newton-Raphson at school, then we're going to get there. There's something like that hidden in here. If you haven't seen that yet, don't worry, that's what we're doing, but, you know, chill. Start with negative numbers. If you start with a negative number, you definitely get a negative number back, right? Because both these terms, x and 5 over x, those are both negative. So if you get negative numbers, you stay negative. If you start with a positive number, you're going to stay with positive numbers. And it feels like maybe you end up at root 5, because that's the point where this equals itself. It's not quite a proof, but not quite a proof, but interesting enough. So somebody who loves both higher dimensions and also loves complex numbers has suggested putting in quaternions. And it's just the multiples of I. They count just the multiples of I that are badly behaved. Yeah. Goodness me. Gosh, it's like boundary break, right? I set up this nice real number problem with, I put positive in, that's a very real number kind of thing, and I was just chucking complex numbers in it. Yeah, it's obviously like y equals x. It's not cheating to have seen something similar before. 90% of maths is about seeing something similar before. Okay, I've got a picture to draw to show you what's going on here. This always gets really close to root 5. Here's a picture and a kind of geometry thing that I want to show you. So my picture looks like this. It's the curve 5 minus x squared. I suppose y equals 5 minus x squared. So this is 5, and chat, you can tell me what these roots are while I try and describe a thing. Let's try and describe a thing. I'd like to find the tangent to this curve at some point on the curve. And I'd like to do that in general, so I'd like to have a kind of variable for where that point is. I think a good way to do this is to give the point a name, to say that this point is at something like, I don't know what to call this. I guess in my notes I've called this B, which seems a bit mad, but I'm just gonna roll with it. You don't like my negative x squared coefficient? Oh, that's not very nice. I suppose you've got a point. I suppose in hindsight you have a point for what's about to happen, but it's nice. It makes the picture look nice. So I'd like to find the tangent there. I love chat. This would not be the same without chat, right? So tangent here. And there's a little bit of standard maths here to say that the gradient of that line would be -2 times x, and x here is b. So that'd be -2b times x minus b plus some sort of constant to make sure it goes through this point, which would be, I suppose, 5 minus b squared. Goodness me, okay, it's quite complicated. Yes, -2b plus c. Yeah. Is that what I wanted? Yeah, -2b like x plus a constant. Yeah, -2bx. Okay, so question, what's the x-intercept? And that's an algebra question to do with this curve, to do with rearranging all of this to say that y equals 0 when, this is why I was getting flamed in chat, I've now got maybe an unnecessary number of minus signs around, and it turns out if you simplify this down, it's this. This is my picture. Yes, okay. So here's what's going on. The x-coordinate of that tangent is exactly the thing that I've been getting you to calculate each time. It looked like some sort of random calculation, x plus 5 over x all divided by 2. But what I was getting you to do really was to take your starting point, your starting number, and to work out the tangent to this quadratic, find the point where it crosses the x-axis, and that's your new number. I just didn't tell you all of the algebra about parabolas and stuff, because I did the algebra and it's quite nice, so I just showed you the answer. But that's the calculation you've been doing. Take your point and follow along the tangent to that parabola until you hit the x-axis. That's your new point. Something really nice that you can maybe see now is that if your point is over on the right of this root, it's definitely going to come in towards the root. The new point that you calculate, the new number that you calculate, is going to be closer. Let's try and draw a big zoom out kind of picture and have some sort of straight line in here that's like whoosh. So you started here, your big number to start off with was like 10 or something. You found that tangent, and because of the way the curve is shaped, I can see that it's going to be sloped like that with negative gradient, which means that I'm coming in. But because the parabola is curved, it's going to curve away from the straight line, and I'll end up somewhere between where I started and that root there. Was it obvious what the root was? The root is root 5. Root 5. No, sorry, just the root 5. Root. So there's a special case where in my picture I've started with a number less than root 5 and it's gone over here to be bigger. But then after that, in general, the numbers will come down towards root 5. It's really nice. So the curvature of that parabola is on the one hand why the point's coming in, because the tangent's pointing inwards, but also why they don't overshoot, because the curve curves away from the tangent. Aha! Good, okay. Something nice, by the way, that you kind of get for free is for so free observation from doing this calculation is that you can kind of see that whatever b is, so long as it's positive, this point that we calculate is going to be to the right of root 5. Wherever I put that tangent, let's try and do it your way around. Wherever I put that tangent, it's going to be to the right of, it's going to cross the x-axis to the right of the curve, which means that this number we calculate will be greater than or equal to root 5. Good, okay. It gets close to, but never actually equals root 5. Because the graph is curved, it's curved everywhere. No matter where you start, you follow the tangent. The graph has just curved away a tiny bit. Yeah, fine. Okay, so x is 0 is a bad starting point, which is maybe why I told you to start with a positive number. But then 5 over 0 would be a pretty bad thing to calculate, so that's all consistent, I suppose. So what did I know all along? Me or somebody else? He knew. Somebody's put. I reckon he knew that all along. What did I know? Or was that someone else? Oh yeah, Newton Raphson or something. Okay, right, good. So in school, you learn this technique in general because it's good. It's a good way of finding roots of graphs. I think it's always presented when you learn it in school as a way of finding roots of graphs, and it's sometimes hard to get a grasp on why that's interesting. I like to think of it as a way to quickly calculate things. So here we've got a method for calculating the square root of 5. Our method for calculating the square root of 5 is something like choose a starting number, like 1 or 10, it doesn't really matter. Work this out a few times, and now you've got a really good approximation to root 5. Those numbers that people were putting in chat before were really good. Oh yeah, sorry, there's a technicality in chat. If you start with root 5, then formula gives you the exact root. So if you start there, sorry, that's an exception. If you start there, you stay there. If you start somewhere else, you kind of miss. Good question, how can we generalise this? So if you don't want the square root of 5, but you do want the square root of something else, the beauty of this is that, I'm trying to zoom out to give you the big picture. On the screen at the moment, it says 5 in a bunch of different places. We haven't used any properties of the number 5, except I guess that it's positive. So something you could do is find and replace, and just swap all the 5s for 37 or something. So up here, there'd be a 37 in the method up here. There'd be a 37 in this iteration version of it that somebody wanted to use. There'd be a 37 here, and the things should get closer and closer to 37, square root of 37, because that's the x-intercept. So kind of all the 5s turn into 37s. So there isn't really any maths going on with the 5s. Can we do some limited epsilon delta business to have square root of 5? We'll keep doing this forever. So if you keep doing this forever, you do get pretty close to the square root of 5. You do get pretty close. You never get exactly the square root of 5. The tangent always misses. I can't really tell if that's clear. It's like leaning I need a sort of pencil or something. It's like having a round object and a straight line. The curved object always kind of curves away from the straight line, so it always kind of misses a little bit. What is this? Somebody wants to calculate. Brilliant stuff. Chat loves complex numbers. What if you put a negative number in? What happens if you put a negative number in? That is a great question. You've seen this idea to find and replace, and you immediately want to try and do it to calculate. So to put it on the board, what if it's x minus 1 over x over 2 instead? And spoilers, this is not going to calculate I for you. It'd be lovely if it did, but it obviously can't do that. It's going to be real numbers all the way through. Something happens though. What happens? And remember, I'm not kind of just interested in the final answer, I'm also interested in the journey. I say that we haven't gone along the way. Is 37 not random enough? Oh, I thought 37 was the most random number. You're telling me that 37 is not the most random number? The margin that misses by is really small. It gets smaller every time you do it. I'd like to analyse that in a second, actually. But I kind of want to talk about fractions. Why does chat love complex numbers and quaternions? Chat, why do you love complex numbers so much? Over to you. Let us know in chat. What is it about complex numbers? I think about a year ago we just had a sequence of several episodes where complex numbers were a good thing to do. That's all ping pong. Right, cool. Interesting. Let's talk about fractions. So, I tried to do this calculation with some fractions. I'm quite lazy, so my starting number was 1, and then I calculated 1 plus 5 over 1 over 2, which is 3, welcome to the Oxford Online Maths Club. 1 plus 5 is 6, divided by 2 it's 3, quick maths. 3 goes to 3 plus 5 over 3 over 2, which gives me 7 over 3, which is pretty good. I'm keeping it as a fraction because I'm interested in the thing Johnny said below, and also interested in other stuff we can do with these fractions, but we'll get there in a second. Around about this point I started getting a bit bored of working out fractions, and I started looking for a way to make these calculations easier on myself. So in general here, if I've got a fraction p over q for my fraction, then what I'm doing is I'm plugging in here and I'm plugging it in here. I'm going to do a little bit of simplification on that to write that as p squared plus 5q squared over 2pq. And in fact p and q are both odd, so that top bit is an even number and it eats the factor of 2. You can simplify a little bit. But what this says is if I've got a pair p and q for my fraction, like 47 and 21, I can plug them into this formula to work out a new fraction. And maybe that's a different way to think about this, to say, oh, if I was doing this with a computer or something, and I wanted to track the fractions, my calculator turns fractions into decimals. It gets bored really quickly and converts them to decimals and then won't convert them back for me. Maybe I could think about doing something like this. I hope you can see what I'm doing here. I'm trying to spell out how you can think about like the vector of those two numbers. Doesn't really matter if you know what vectors are. Like I could store them separately, 47 and 21, and explain to my computer, well, the thing you need to do is work out the first one squared plus 5 times the second one squared, and separately work out 2 times the product of those two numbers. And you don't have to tell your computer that they are numerators and denominators of a fraction that's approaching the square root of 5. You don't have to tell it that. Instead, you can just store those roots, and then at the end, you can work out the square root of 5. You can write down your fraction. This is maybe a good trick because computers are a little bit better at storing integers than they are at storing fractions. People in chat say they like complex numbers because they can go in basically any formula to derail the episode. Thanks. At least we're honest, you know. At least we're honest. Divergence, periodic behaviour for that one. Oh, question: does it work with other numbers? And answer is yeah. Other positive numbers. Yeah. In general, the argument with the quadratic just works with other numbers. You really do just replace all the 5s with 29s or whatever you want. Cool, okay. Oh, it looks like Man's already got it calculated out on a sheet of paper on the table. Yeah, sorry, for this bit I do. I didn't trust myself to do these fractions live. So yeah, you called me out, dude. I've got fractions on this bit of paper. Use Wolfram Alpha run the calculator. Can Wolfram Alpha do good fractions? Is it handling fractions well? I guess Mathematica does. So yeah, wouldn't be surprised. 5 with a negative number. People in chat are currently trying replacing 5 with a negative number. To be precise, they've replaced 5 with the number negative 1, and they are reporting back what's going on. If you want to join in, all you need to do is pick a number and start working this out repeatedly and see what happens. Or grab a calculator, put in a number, press equals, and then type in answer, take away, 1 divided by answer, all divided by 2, and just see what happens. It's definitely not going to converge to the square root of -1 because that's not a real number. Your starting point number was 5 and you got the same fractions. That's good. That's especially good news for my little bit of paper where I've got the fractions written out. Yeah, sorry, maybe I did that bit extremely fast in a way that looks rude. Is there a thing for cube roots? There we go. That's the sort of question we ask on this stream. Is there a thing for cube roots? Hopefully in the next 10 or 15 minutes we will have a thing that works for anything you like. There's a bit of art to it though. Oh, somebody wants to just replace the 2 with a 3. Right, let's go. Okay, let's go. Let's learn Newton. I think we've now got the motivation for learning Newton's method, right? If you do A-levels or equivalent, then I think at some point you learn this sort of maths. What you maybe don't get is a reason for why it's a good idea. Do people in chat know this? If you've already seen Newton, we're about to learn it. You don't have to teach Newton in chat. I'm about to explain what Newton's method is. But have you been told why it's good? I don't know, maybe that sounds like a value judgment, right? But there is a reason why it's good. Where are we going? We're going over here. Sorry, that's quite jumpy. There we go. Going over here to learn about Newton's method. Newton's method says this. It's kind of like the same thing we just saw, except instead of a quadratic, Newton's idea is to do that for a general function, which could be hard, but let's try and do that. Okay. How am I doing for time? My bit of paper has already also got timings on it. Oh, fair enough. Fair enough on timings. That's all right. What on earth am I doing? I've drawn a function with no roots. Terrible start. Okay, let's do that. Okay, that looks great. Newton's idea is that if you're trying to look for the root of a function, you've got some function f of x. The root of f of x equals 0. That's what's going on here. Then something you can do is start with an initial guess. I'll call that x1 over here. So this is f of x1 up here for the y coordinate. And what Newton's idea is to find the tangent to that curve, which could be difficult depending on what the function is, but find the tangent and find the point where the tangent crosses the x-axis. Those steps that we did before, find the tangent and then find the x-intercept. Right, okay. In general, the maths here is a little bit awkward, but we're going to give it a go. The tangent, and depending on how much differentiation you've seen, you might just need to take it as read, I suppose, that this is not terribly awful to work out. A little bit confusing, perhaps. The tangent involves, in general, finding the derivative at that point. The tangent has got the same derivative as the graph. I'm writing down something like this for the equation of a straight line. Wait a minute, it's got to go through that point as well. And this is how I like to write down my equations of straight lines. X minus x coordinate times the gradient plus something else. Oh gosh, that's f of x1. And then the x-intercept is when y equals 0, which is when, oh gosh, where is that value of x? And then there's a bit of rearranging to do. So if you go and rearrange that, skipping some of the algebra, it turns out that the x-intercept, which I suppose I'm going to call x2, maybe I'll call it x2 in a minute, but x is going to be equal to x1 take away f of x divided by f prime of x, 1 inside here. So if you know x1, then you can work out where this next x-intercept is. Newton's plan is that you call that x2. And then keep going, keep working that out. This could be really difficult, especially if the gradient of f is a hard thing to work out. If you're just starting A levels, then you don't know how to find the gradient of very many functions at all. But if you do, then maybe you can turn this into a sort of general rule. Let's catch up with chat, which I've got behind me. Yeah, it's one of the last things you do in the second year of maths. So depending on what order you're learning this, you maybe haven't seen this before. It never seemed useful. Okay, so nobody's told me why it's good yet. Goes all over the place, but possibly converges to 0. I'm suspicious of that, because if it gets close to 0, Michael's talking about x plus 1 over x, or sorry, x minus 1 over x. If it gets close to 0, then that 1 over x term is going to be huge. So the next thing you see is probably not close to 0. And then maybe the thing after that is also huge? Oh, I don't know. Okay. Does this work for repeated roots? Yes, but it's a bit less good. Oscillating around 0. I kind of want to try it now. I've got a calculator in front of me. Sorry if you've been doing this for the last 10 minutes, but I sort of want to see what happens if I put in answer take away 1 over answer. The thing that I got chat to try out for me. Oh yeah, gosh, crikey. Yeah, that's doing some horrible stuff. That's really unpleasant. I don't like that at all. Yeah, and mine is sort of, oh, I felt like it was escaping there. Is it escaping? Oh gosh, that's all over the shop. Brilliant stuff, love it. Would highly recommend trying that out. Yep, we're over here. Would highly recommend. This turns out to be amazing. I love it a lot. Right, good. Newton's method then. Does this give you a quick and dirty way? Yeah, it's pretty quick. Pretty dirty. I mean, if your function's not a straight line, like we've been talking about how that quadratic's not a straight line, then it doesn't give you exactly the right answer. Maybe you need to do this again. So doing this again would be like looking over here underneath and finding the gradient and the tangent. It sounds like a lot of work because you're doing some sort of geometry stuff to find the tangent and the gradient and, oh my goodness, the x-intercept. If you know f, and if you know f prime, the derivative, then sometimes you can simplify this. So for the quadratic, 5 minus x squared, this says that the rule is you do x1 minus 5 minus x squared over minus 2x. I really regret those minus signs now. That comment in chat about having too many minus signs in has really it's really hit home. One of the most accurate criticisms ever. Wow. Which is the formula we had before. Somehow these two lines, which are probably the most mysterious lines of all, contain all of the geometry about finding tangents and things. That's the thing that Newton was up to with this. Oh yeah, it is the Newton, by the way, same Newton. Okay. So personally wanted cube roots. I said about 10 minutes ago that I hope we find something for you to find cube. How long have I been muted? Oh no. When did that happen? How does that happen? That's very embarrassing. Sorry people. If you're watching the live stream, I might remove that. Whoops. My bad. Not 10 minutes. Please not 10 minutes. Whoops. Less than 10 minutes. Maybe? About 15 seconds. I'll take 15 seconds, that's acceptable. It's because spacebar is mute when I've got certain things selected. Sorry, chat. G'day. Newton contains all of the ideas about the geometry. Cube roots, thank you very much, that's the line. Write out an equation like this. It's a bit weird that you've got to turn it into a root finding exercise, x cubed minus 29, and then your method will be the following. To look at x minus, and then the thing up here for you is x cubed minus 29 divided by 3x squared, which says something like, gosh, if I'm trying to find this, then I need to look at 2x plus 29 over x squared over 3x squared. So somebody said, do you just change the 2 to a not x squared? Over 3. Can't do maths fast enough in my head. Ha! There we go. Somebody said, do you just change the 2 to the 3? And yeah, sort of, almost. You need to balance out the factors on the top a little bit as well. I don't really think about it like that. I think about it as plug it into Newton. Use this general expression with a carefully chosen f. So I think my claim is that this thing, choose any starting number that's positive, calculate this a lot, and it should go to the cube root of 29. Who knows? If true, it's a fast way of working out cube roots. I'm saying fast a lot, which is part of the reason why this is good. Thought I might like to try and show you that. It's definitely more advanced than A level. I remember learning this in A level, and we did not learn that this was fast. By fast, I mean as you keep pressing equals in your calculator, or as you keep doing this expression, you get closer and closer to the cube root of 29 or whatever, with very few button presses, very few equals presses, and your calculator doesn't have to do very many calculations to get closer and closer. Yeah, good questions in chat as well. Okay, so I think I'll show you why it's fast, which is a little bit of university maths, in a second. There are lots of things that can go wrong. I drew this kind of wiggly function to show you what could go wrong with this in general. And I love this, look. If there's two roots, no guarantee that you'll converge to the one that you wanted. No guarantee that you'll get close to the one that you wanted to get close to. And if your first guess was over here, maybe you get a bit stuck. It's not obvious. So maybe if your first guess was over here, then maybe your next guess is also on the left. It's a bit hard. Then down here, you're going this way instead. You get a bit confused by this. Guessing around here is pretty bad because the tangent hits somewhere over here, and then you're going the wrong way. You're not finding that root. So Newton's method only works sort of near the root in general. It doesn't in general work for any starting number because your function might be really complicated. It's particularly bad if f prime is 0 at some point, because then the algorithm says divide by 0, which you should not do. We've only got 2 rules on this chat: don't swear and don't divide by 0. What's the fast bit? I'm not sure if the epsilon analysis stuff has ever been in A-level. Let's do that now. Okay, I'm going to get sidetracked. It's what you know and love, Maths Club 4, right? We're off script, a bit of paper. Here's why it's good. Let's focus on this one first, this one that I was getting you to do. Here's why is this a good idea. So, reminder, we're working out x plus 5 over x divided by 2. And the observation is something like if you're near the square root of 5, then the next time you press equals, you get even closer to the square root of 5. I'm going to try and demonstrate that with some slight. I'm nervous because it's slightly scary maths, right? Let's do that over here. So, if x is equal to square root of 5 plus a little bit, what is, and then we're going to work out x plus 5 divided by x all over 2. And for traditional reasons, instead of writing out a little bit every time, I'm going to use the Greek letter epsilon, which is a bit like a curly capital E, I guess, or like a weird E shape. It's the Greek letter epsilon. Maybe I shouldn't call other alphabets weird. It's not very friendly of me, is it? Right, okay. So if x is equal to root 5 plus a little bit. Okay, if so, we can plug that in and find out what happens. What I want to examine is, this says that x is pretty close to root 5. How close is this next thing that we're about to work out? This is a sort of analysis that we do quite a lot in these, in cases where we've got this repeated iteration sort of thing, and it's converging, it's getting close to something. We might ask questions like, how close is it getting? So then this thing we're working out would be this. And now I've got a bit of a problem. I can't simplify this very much unless I deal with this 5 over root 5 plus epsilon. So I'm going to do 2 things. I'm going to pull out a factor of root 5 on top and bottom, and then indeed out of the whole thing. I'm going to write that as, I think I can write it like this. So just this bit here. I'm going to pull out a factor of root 5 and write it like this. The reason is I know an approximation for this expression, 1 over 1 plus x. Actually comes from geometric series. So if you've seen geometric series, then have a think about this afterwards. But this is a bit like this, with some more terms in there as well. Now that might have looked like it's just come out of a hat, right? 1 over 1 plus x is some sort of weird, you can write that as being a little bit like 1 plus a correction, a tiny bit plus. This is a tiny correction, it's like epsilon squared. If epsilon is small, epsilon squared is tiny. So that's maybe come out of a hat, but at some point if you learn about, this is called the binomial expansion, right? Good, okay. Let's write that over here. I like to label these things in case, if you've seen it in school already, like with Newton-Raphson iteration, if you've seen it in school already, it's a reminder that it's something familiar. If it's unfamiliar, then that's fine. I'm not trying to make it more scary by putting words on it. Who knows what that means? It's entirely possible you haven't met this yet. Anyway, If I plug that in back up here, then this is roughly equal to, roughly because I've got this dot 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 over here, that these things, I'm not claiming these things are exactly equal, they're kind of pretty similar for small epsilon, is equal to root 5 plus epsilon plus root 5 minus epsilon plus epsilon squared over root 5 for 2, I think. And then beautifully, loads of stuff cancels. This epsilon cancels, and it cancels over there. So this thing here would be root 5 plus epsilon squared over 2 root 5 or something. So most of this maths doesn't really matter. The punchline is supposed to be that if you started very near to root 5 plus a little bit epsilon, then after pressing equals on your calculator one more time, via the magic of binomial approximations or whatever, you're now at root 5 plus something like epsilon squared. So if your tiny bit was, you were within 0.1 of root 5, you were really close. You got the first digit, spot on, you were at 0.1 out. Then after pressing equals, that's about 0.01, like the square, right? And then you press equals again, and it's like the square of that. And squaring small numbers, they get smaller really fast. So these things are, these things get small really fast. Yes, thank you so much. It is a geometric series with a corner ratio negative epsilon over root 5. So the sort of thing that's not very helpful for me to say, but if you know what that means, then it's a helpful thing to notice. Anti-quality. Oh, I like that. That's the sort of nonsense that I might say. Anti-quality symbol. Yep, all right. I sign up for the anti-quality symbol. No, wait, that sounds bad. I'll call it the anti-quality symbol. That sounds good. It's like 1 over x squared. Yeah. Which bit? Yeah, a little bit. Yeah. Okay. Punchline at the end then. Small difference to start off with gets squared. I really just want to show you what squaring does to small numbers. This is obvious, I know, but just let me be excited, right? Squaring for small numbers does stuff like this. 0.1 goes to 0.01, goes to 0.0001, goes to 0.0000001. Right? So these differences, okay, there's factors of 2 and root 5 in there, which I don't really care about, but like the magnitude of this difference gets small really fast. Somebody in chat is going to tell me that I put the wrong number of zeros, but I think I've nailed it. There's 8 zeros and 16. That's just inviting mistakes now, isn't it? 12, 13, 14, 15, 16. Right, it's just like these differences are really tiny, really fast. Which is why you press equals and the digits get locked in quite quickly as you're pressing equals. The first ones change and then they stay the same, and the later ones lock into place. It's a little bit like every time you press equals, you get twice as much accuracy. That's mad. That's really crazy. Okay, I don't think anyone tells you that at A level. The reason Newton's method is good is that because every time you iterate, you get twice as many decimal places as you had before. And maybe it's worth thinking like that. If you set this up right, this is like having a machine that runs some code, and every second it spits out digits of pi. That machine's already impressive. Because it's getting more and more accurate. Every second it spits out a digit of pi. Newton's method, though, is like a machine which every second it spits out as many digits of pi as you already had. So first it says 3.1, and then it says, after the next second, 4.1, and then after the next second it says 59265, and then after the next second it says 9326538, and it's like it does more and more digits every time. Passing comment, but not actually shown. Yep. This is called, because of the squaring down here, this is called quadratic conversions. It's something that I've been teaching to first year undergraduate students last week. So we've gone a little bit off track. We've gone a little bit into first year undergraduate maths. It's really good. It's really good. I think this one is really good. Yeah, okay, so Newton in general. If it's working really well. If it's not working because you divide it by 0, then it's not working at all. Yes, it's a bit difficult to do. Quadratic with roots plus and minus pi is a bit hard because along the way you might need to know pi for your calculations. If you're using radians, you can do something with cosine, I think. There's something you can do with cosine if you're using radians to work out pi over 2. And then this is a sort of machine for really accurately calculating pi. Let's put in cos 2x. Yeah, okay, let's try and build that. So the function would be something like cos of 2x in radians, which has got a 0 at pi. And the machine would be something like, take your initial guess, and then go to cos of 2x divided by 2 sine as a negative sign in here from the derivative of cosine. So it's not really appropriate for me to do this live, I guess, but hey, I reckon that works. What am I claiming then? That's x plus cos x 2x over 2. Something. Maybe that converges to pi? Wouldn't be the maddest thing to converge to pi. My calculator ain't got a cot button. I'm going to have to use tan, aren't I? Let me know in chat. I'm going to do this, but let me know in chat. If you repeatedly calculate x plus 1 over tan 2x with 2, do you get closer to pi? Be good if you did. Does that converge to 3? You need a 2 in front of that first x. With cubes, so with the function x cubed, you end up, just from the way Newton works, you end up with a factor of 2 just here. And actually an x squared over here. Slightly different. I'm not sure what the thing you're describing would converge to, actually. I don't know where it comes from. Why is maths easy to learn and then forget? And there's loads of it, which helps. Can have a math club sometime focus on the hardest step questions ever written? Sounds like a challenge, right? Sounds like a challenge. That person really wants a math live stream. A quick reminder, do not execute arbitrary code that you got from a live stream. If you do execute arbitrary code on your machine that you got from a live stream comment, then we're not responsible for anything that happens. Right, good. Are we still doing -1? The one with -1 jumps around a bit randomly, but occasionally makes a big jump up. And then I think it comes back down again, but I'm not sure. I think it's really interesting. Who invented this? Does someone want to take credit for this? Someone should take credit for this. Oh, instead of cos, do I mean sine? Ah, cos doesn't give the right roots. Do I mean sine? Sine would have been a cleverer thing to say. I tried to do cos 2x. Sine would have been a cleverer thing to say. There's a little bit of an art form to choosing which f you're going to use. So that, oh yeah, that looks really clever. Does that work? That doesn't look like it could possibly work. So just x plus tan x. Ooh. Comes back down and then does something mad again. She's got this weird energy. I think that's my favourite thing. A thing that today is supposed to be about getting your calculator quickly calculate things. It seems like we're doing something that operates very slowly and doesn't calculate anything at all. But that's the joy of this, isn't it? Let's see if I can hit this. I need to be in. Oh gosh, it's very, very silly to try and do this live. Let's try and do this live because that one looks interesting to me. Answer plus, what's 50? Answer plus 10 answer? That doesn't look like it could possibly work at all. I don't know what that's doing. It's not working at all. Don't like that. It's very, very slow. Doesn't look like it's doing anything fun. Okay, I think I've made some sort of weird mistake somewhere. Because this is just going up, right? Oh yeah, okay, I'm in degrees. Okay, cool. I'm an idiot, but people can maybe try that out. Chat maybe thinks... I am an idiot. That's converged to pi over 4. It's because I put the 2 in the wrong place. I'm so sorry, chat. Try this one instead. This one looks better. This one looks cleverer. Gosh, I squashed it the wrong way. That's embarrassing. Good thing that wasn't recorded forever. First one with half, not 2. Thanks, chat. Yep. That would have a root when x is pi over 4. Good-o. Right, okay. What are we doing? It's 6 PM. We've got about half an hour. Do you think it should be x minus tan x? Well, Newton's got a minus sign, and I thought I got another one from... Yes, you're right. This is not a successful not a successful details-oriented live stream. We've got the big picture, but not the... Yep, derivative of sine is cosine. Thanks for coming along. Your contribution is always welcome. This would be so different without chat. Without chat, I would be making these mistakes with plus and minus signs and factors of 2, and no one would notice. That's maybe not true. People let me know in the comments. X minus tan x, and remember to set your calculator to radians. Does that work? We're going to try it now. We've done a little bit of crowdsourcing. I'm going to try and work out how to set my calculator into radians, which I thought I had, but no, I have no idea what I'm doing. This is not really my calculator. It was just in the office. We think that if you pick your favourite number and then continually, maybe nearish, maybe not too stupid, so that this isn't dividing by 0, but if you repeatedly work out x minus tan x using radians, then you get closer and closer to pi. Of course, separate question hidden in there before we get too excited is, how does your calculator work out tan? Your calculator has a tan button. How does the tan button work? And there's this moment, I think, where you look at your calculator and you start to realise, is my calculator doing some sort of approximation, right? When I press equals on my calculator, it looks like it's just doing one sum because it shows me the answer. But what if secretly, behind the scenes, it's doing lots of calculations and then showing me the result? What if when you ask it for the square root of 5, what if behind the scenes it just does that thing we started with, just does the thing we started with, and then spits out the answer that it gets? That would work, right? It's not obvious that your calculator's not doing that. In fact, there are other methods. Oh yeah, you might end up near a multiple of pi. Oh, look at this. That is great typing, well done. Thank you very much. Okay, I want to show you an algorithm that uses this. It's a little bit famous. In the further reading notes, we're going to link to a YouTube video that explains it much better. Oh, on that note, are people aware of further reading? I used to mention it every week and that got boring, so I stopped mentioning further reading, but people know about further reading for this? Most weeks come with further reading that gets typed up over the weekend or sometimes the following week. There are some notes, so if you're interested in an episode, you can check back later and get some further notes on that. People know about that? Yeah, no, someone just says yes in the sort of possibly saying yes, we know about further reading. Stop talking about further reading. Cool, right. There's some slightly famous code. So this is from Quake Engine, and it's an algorithm for working out 1 over the square root of x. Which you have to do sometimes for things to do with normalizing vectors. So if you have a vector and you want it to be unit length, you need to divide by a squared plus b squared, divide by the length of the vector. You work out a squared plus b squared, and then, oh no, you would like 1 over the square root. Is that converging? There you go, it's giving you the same answer a few times now. Brilliant, good, that's converged. There's a step in here, so the code is semi-famous for having this bizarre constant in the middle of it, which I'm not a computer person, but seems a bit mad to me. It has a semi-famous comment on it as well. So this is the programmers needed something that would do 1 over square root of x. There's 2 stages to what they're doing. There's a computer science trick and there's a maths trick. The computer science trick I'm going to leave in the further reading. There's this stuff in here. This works out a sort of initial guess. It's a really good initial guess. It uses this weird number, it does some sort of conversions between integers and floating decimals. It exploits the way that numbers are stored in binary and how we're looking for the square root. Square root involves the number 1/2. 1/2 is good in binary. This method would not work if they were interested in 1 over the cube root of x, because the bit shift wouldn't work in the same way for dividing by 3 as it does for dividing by 2. So there's something in there. Why have I got rid of the comment? There are 2 rules in the live stream. Don't swear and don't divide by 0. Yes, there's something clever going on there for an initial guess. This is the kind of CS bit of it, where it's doing some hacky stuff to get an initial guess for 1 over square root of x. But then there's this really nice bit in here for this iteration. To iterate, this line's commented out, or it says can be removed. But these lines, which are the same, are Newton-Raphson iteration. Okay, and then it returns y at the end. Good. Yeah, it's like it's in Quake. I'm hazy on the details, I'm not really a computer person, and I know that I'm going to link you to a YouTube video of somebody explaining it really well. I just wanted to demonstrate the thing about it doing some maths down here. Where's this 3/2 bit come from? That's the bit that we sort of stand a chance to understand with what we've done today. The idea is not bad at all. The idea is to use Newton on, I believe, the function. So if we want to solve this, which is a little bit awkward that I used an x up there, but I'm going to sneakily delete that so it's less confusing. If we want to solve this, then maybe we could think about doing something like a minus 1 over x squared. Let's do let's do a minus 1 over x squared as our f of x. Do I want that the other way up? No, I'm questioning all my minus signs now. You got me questioning them. If that's our f of x, then the root will be 1 over the square root of a. And Newton's method says that we're supposed to work out for our iteration x minus a minus 1 over x squared divided by, and then the derivative of that is minus 2 over x cubed, which just simplifies really nicely. Newton says calculate this thing repeatedly. So if I rearrange this a little bit, then we're going to get something nice, right? We're going to get something nice. I believe in myself. We're going to get something nice. Yeah. I've gone really, really quiet because I don't believe in myself. Let's do it really slowly. Yeah, no, I should believe in myself a bit more. This is good. No, it's bad. It's minus signs. There's a minus sign here. So there's not been the live stream for minus signs, has it? It's been, if anything, the worst live stream for minus signs. Okay, I think we're getting there. Brilliant. Okay, so this is what's going on in this code. This is what's going on in this code. They've got the number y as their previous guess for the square root. So that's their kind of starting point. In my algebra down here is the number x, because I was thinking of it as the x coordinate. And they've worked out that thing multiplied by 3/2 subtract, and then this thing in here, x2, is half of, here it is, half of the original number they wanted. So like the target to be input to the function divided by 2. x2 times y times y. Okay. So that step of Newton in there is just from doing Newton to a kind of pretty straightforward f of x, which you learn about in A level. Hooray! The thing that makes me laugh about this code, I don't know if there's a reason for this, but I just find it amusing that somewhere in here they define a constant, which I've been led to believe is best practice. You know, to define your constants at the top, they define the constant 3/2 to be the float 1.5, and they define that so that they can use it down here, which I think is nice. It's nice to define that up here. They do not define this constant. It just appears in the middle of nowhere. What the black box. So I don't know why they spell out 3/2. I guess maybe it's because they're going to use it twice. Goodness me. Does Oxford Maths have a trebuchet? Yeah. we should acquire a trebuchet. We've been around long enough that we should just have one lying around, right? From back in the day. 800 years, right? Is that long enough to have a trebuchet? Or is that a different thing that I don't know about? Can you plug in vectors and matrices? Oh, into here. I think this code is not good for that. And while this was brilliant at the time and works really well for the time, it's been replaced by hardware. There's now a kind of chip level thing that does a better job of working out 1 over square root x, that avoids having to do quite so much multiplication. There's like quite a lot of multiplication down here, quite a lot of operations for your computer to do. I think it's now a hardware thing. Again, I'm not a computer person. They're using 3 halves maybe more than once. Yeah, I guess this line's commented out. Oh, is that best practice if you're going to use it twice to give it a name? 3 halves. If you're going to use x2 twice to give it a name. I see. I'm learning best practice. What's this useful for? Oh yes, this software is for working out 1 over square root x. The classic thing is if you're doing kind of anything with vectors, but I suppose if you're doing things with reflections, so you're trying to make a graphics engine or something that models like reflections off surfaces, or you're trying to work out just how far away things are. Oh no, yeah, that would be square root. 1 over square root comes in when you're normalizing things. It's just quite often that you've got a vector x, y, z or something in 3D, and you want a unit vector. So you want x, y, z divided by the square root of x squared plus y squared plus z squared. You just kind of want that quite a lot. That could be some sort of normal vector, so that as you're doing your calculations for this bounce, you've got like a little normal vector in the direction normal to the wall. Again, I'm not a computer person. I don't write this sort of software. I don't write any software. Why did I put that caveat in there? 2 steps here, work out x squared plus y squared plus z squared, and then pass that to this function to work out 1 over square root. Okay. Yeah, it's a really weird hexadecimal number. It's super weird. It comes from, it could be something slightly different that's easier to explain. The thing is, it's being tweaked a little bit to make that initial guess better. In some sense, it's an attempt to make this code better by having a better initial guess, which is a relatively great idea, actually. You're going to run a round of Newton on it anyway, and Newton iteration is really great, so it doesn't matter maybe too much, but there has to be some sort of constant there for reasons to do with this weird computer science trick that they're doing. And if you're going to put a constant there, you might as well put the best constant you can. And that's an attempt. I'm not certain it's the best. It depends how you define what best means, but I think there's some sense. Why can't you use a calculator? Yeah, so yeah, it's pretty slow, isn't it? Bouncing, right. Petitia's off. Bye. Let's see. Or Petica? Petitia. I'm going Petitia. Chat is about to discover that I don't know how to recognise whether things are C or C++ or C++ or C sharp. I can't tell the difference. Today's episode was suggested by a current student who did the research for me to find out lots of stuff about Heron's method and Newton's method. Oh, they told me to call it Heron's method. Way over here. That reminds me. This is called Heron's method. The square roots. So yeah, they told me to tell me what to cover, and they looked it all up. They were more interested in computer science than me. So shout out to Zach for doing the research for today's episode. Zach knows loads of stuff about this. Oh, Petica, sorry. Okay, there we go. See you next time, Petica. This is way faster than some of the alternatives. There's kind of 2 things about why not just give it to your calculator. One is you want some sort of control over what's going on. Your calculator is going to do something. And if you look inside your calculator, maybe you could find out what it is. Maybe you could tweak it and make it even better for your own needs. The other thing is that you need something that scales really well. This one doesn't do this, but modern things like this can accept multiple numbers at the same time. They can do this kind of parallel processing stuff, which my calculator can't do, at least. Getting down to that kind of exploiting hardware kind of level. If you want to calculate it really fast, because you're doing a lot of ray tracing and you're doing a lot of bouncing or whatever you're doing, you need to do this calculation a lot of times, then you've got to get down to the nuts and bolts. No good delegating it to calculators or existing routines. You probably want something in hardware. This is not hardware. Okay, right, good. I think I've managed to say enough without completely embarrassing myself on the computer science bit. Sorry, Zach, thanks for doing all the research on the computer science bit. What did I want to do to wrap up? Yeah, I wanted to try designing other stuff. So, big aim of mine is to try and get a good approximation to the 12th root of 2. I think it'd be really good to have a good approximation to the 12th root of 2 for like music reasons. This number's important in music. It's something to do with tuning semitones. So there's a little bit of a hard problem here to choose an f of x that lets me calculate approximations to this. Choose an f of x that gives, via Newton below, approximations to the 12th root of 2. There's a bit of maths and science here from actually choosing it and following through, working out x minus f divided by f prime. There's a bit of maths there, but there's also a little bit of art, or a little bit of choosing carefully to choose what you're going to pick. Different functions f can behave in different ways, even if they have the same root. Maybe you could imagine that if this is the number we're trying to calculate, you could have several different functions that go through that point that have that root. But some of them might be more wobbly and bumpy and confusing. We talked a little bit about how Newton's method can get confused by things like this, where there's a separate maxima or even worse, a sort of hill or turning point. Yeah, so the first thing I tried was something like that, 2 minus x to the 12. Yeah, plug it in, give it a go. Does it give me useful approximations to the 12th root of 2? I found that it gave me, well, I'll let you try it at home, I think. And maybe you've got other things you want to approximate as well. We had a go at approximating pi. Can you come up with other things? There's something quite nice here in iteration as a way to quickly calculate constants. 2 is a pretty good approximation, is it? For the 12th root of 2? I'm not sure about that. I'd quite like to get a couple of decimal places, ideally with a nice fraction. Yeah, so there's Newton's method, I think. It's got a power of 11 in there. Is it that way up or is it the other way up? Something, oh my goodness. Something, goodness me. So there's a question there, if you want to try and calculate other things. I'm trying to think of follow-up questions now as we get towards the end of the hour-and-a-half live stream. It's a question that maybe if you choose a different f of x, do you get a better approximations? Who knows? It will all work faster. If you choose it properly, then you actually get to the right number, not pi over 4. I'm still impressed by this. I had a sneaky go on my calculator while I was talking earlier, and I couldn't work out what was going on. So as soon as this live stream is over, I'm going to go and work out what's going on with x minus 1 over x, all divided by 2. Is it getting larger or smaller? Negative, positive? Who knows? Somebody's just told me that you get 476 at the 148th repeat. So they've got some large number after a while. I see, but then it gets divided by 2. So if you've got a very large number, then the 1 over x doesn't matter and it's getting divided by 2. And if you've got a very small number, then the 1 over x says, whoa, now it's enormous. And the sign changes. So at some point in between, it's getting smaller and then getting larger. Maybe there's something in between. Something you can sometimes do for these is you can look for fixed points, things that stay the same. Wrap up in a minute. There we go. That notification says that I've got back on the internet. I think I'm tempting fate by staying live. homework then, if you want some homework, is to find out what on earth is going on this. Doesn't tend to infinity. Or does it get really big, or does it not? We were not live for a second, but then we were live again. I only realised because my camera froze on the little preview. Sorry about that. Sorry about the tech today. Sorry about the minus signs. The other thing I want to point out for a follow-up is this method of tracking it like fractions. You remember Johnny mentioned fractions a while ago. Tracking it with fractions and tracking the numerator and denominator separately. That gives you an interesting way to just work with whole numbers on the way through. And you get close to whole number solutions to equations in a way. There's a branch called Diophantine equation, branch of maths called Diophantine equations, which this is related to. Okay, any last questions about what we've done today? Or I guess I haven't been taking that many questions all the way through, so any first questions about what we've been doing today? Or if anybody wants to chat about admission stuff, then I think I've got 8 minutes here because I've run out of Newton. Have I run out of Newton? Oh, I was going to show you a cube root thing. Let's see if I can find the cube root thing. Where am I going to find the cube root thing? I think I got rid of it. Let's see if I can find the cube root thing. There's a really good expression that calculates cube roots really fast, which I wanted to show to you, but I can't find it. Oh no, I will find it. This is going to work. Yeah, this is a good way to wrap up as well, because even more mad than all the other things that we've done. Goodness me, how am I going to get it? There we go, and then it's here. So this is from the end of a question sheet that my students have been looking at recently. It is gorgeous, and it's for calculating cube roots. Somebody asked about cube roots. We had one go at it with the function a minus x cubed. I think we put 29 in there or something. There's one that my students are working with at the moment, which is this 5xn plus 5c over xn squared minus c squared over xn to the 5 calculates the cube roots. And it does it really fast. So something in there. 1,000 iterations, so it's got up to about 1,000. Feels like the way some random number generators give you a distribution that gets up quite large. Doing AS further maths this year. Sounds like good exam preparation at least. Is that going to help? I mean, if you get top grade in it, it shows that you're on track. Oxford, and these days I think most universities, we don't get very many AS level scores because lots of people don't do AS levels anymore. So if you do it, I hope it's good exam preparation, but if you're not doing it and you're watching this, then if you're not doing AS level further maths, then don't stress. After 1 million iterations, it is roughly 20% of a million. Which is consistent a little bit. Yeah, so this is mad, right? Where does the 5 come from? Where's the 9 come from? What is going on? Who chose these numbers? Where's the xn to the power of 5? This calculates the cube root of c. It does it super fast. It's really good. I think it might be better than... If any of my students are watching, don't listen to this bit. I think it might be better than quadratic convergence. I think it might be even faster. They're supposed to be working out how fast it is by doing the kind of analysis to look at the difference between this and the cube root of c. But that's homework for them, I think. How much coding is there in the maths degree at Oxford? We teach people a little bit. We're more interested in the way... Not very much. A little bit. And we teach it. We don't expect people to have coding experience before maths degree at Oxford. For some of the students, it's the first time they've done any coding whatsoever. Students, are these students from a certain college? Oh, my students. Whenever I say my students, I mean roughly 6 students who are at one of the colleges I do tutorial teaching for. I've just been doing tutorials on this topic. Hooray! So we've been meeting up once a week to talk about this sort of thing. I teach, at the moment, at time of recording, I teach at New College, which is one of the oldest colleges. It's like a joke, I guess. It wasn't a joke at the time, but it's got parts of the old city walls in. It's a nice college. I'm saying currently at time of recording because things can change over time. Every college is the best college. Right, good. Okay, I'm going to point at this a little bit. It's not even obvious that if you're at the cube root of C, you get back the cube root of C. Even that is a bit of a faff to calculate. You put in the cube root of C here and here and here. Oh my goodness. It kind of just about gives you 5 and 5 minus 1 is 9. Oh, divide by 9 gives you back the cube root of C. So it's not even obvious that when you finally get to the cube root of C that you get back. Much less that if you do this kind of expansion of like... so the thing there's maybe doing at the moment is... what if you're at cube root of C plus a little bit? What happens next? And they're going to maybe think about doing binomial expansions on this thing and on this thing to work out how close you are to the cube root of C after the next equals press. Oh, actually that question, I've reread it. That question is, which college did you go to? And I went to Trinity College. Similar things for other roots. Yeah, part of the fun is trying to design these things. So you can design them, one way to design them is by choosing a function that has roots in the right places, like up here, pink circle. Up here, we had a function and we rearranged it to be a root finding exercise. And then Newton is really good at root finding, so we put it in here. This rule, via some sort of argument about geometry and tangents, this thing tries to improve your guess by following the tangent down to the x coordinate. There's other things you can design though. I think this one might have been designed just by choosing the coefficients to have certain properties. Can you use, and then I don't know what those things are, to show you have the fastest possible method. I think in this branch there's always a faster method, I think, in terms of convergence rates. So I'm not sure that's quite a thing in the way that you want it to be, but you know some computer science words that I don't know, so I'll let you be the judge. Cool, right, I can feel it's turning into a computer science live stream, which is, ooh, I am not the right person to be presenting a computer science live stream. The computer science department would be the right people to present a computer science live stream. Right, okay, we've got things to try at home. We've got further reading, which apparently I mentioned quite a lot. Do check the further reading if you want to find out more about the topics on here. Today's episode, the research was by Zach. Thank you, Zach, for researching. The presenter was me, and comments were moderated by me as well. Hooray! We'll see you next week for another episode of the Oxford Online Maths Club. Remember, don't swear, don't divide by 0. Take care, stay safe. See ya. God, that sounded awful. This was like life advice. Really terrible. I haven't even turned it off. It's still going. Right, good. Take care. See you around.